Swayam Prabha. Digital India. Educated India.
Good morning, everybody. Welcome to this fourth lecture of Module 1, where we will be discussing vacuum process applications. In the first three lectures, we have discussed basic concepts, units, and then classification of vacuum ranges, and some natural vacuum, some importance, popular topics we have discussed. Right now, you may be wondering why I am jumping to process applications, because the course itself is 50% vacuum technology and rest 50 is process applications. So, just like we have introduced vacuum technology in brief, I feel it is better if we introduce process applications also in brief, so that you will get a feel which level of vacuum is used for which application briefly in the beginning itself, so that when we cover these applications in detail along with techniques and instrumentation and principles and design, etc., you are already mentally prepared that I am going to have this level of vacuum, these are the materials, etc. Some bit of appreciation towards design principles involved in various process applications, you will get a feel of it in these two lectures, that is lecture 4 and lecture 5. They are dedicated to introduce basic concepts or physical concepts or even physical principles involved in various process applications. Okay. What are the concepts covered in these two lectures? The background principles as well as different varieties of industrial applications. Starting from classical applications like chemical, pharmaceutical, food processing or mechanical applications, right up to high-tech applications like chip manufacturing, electronic computers, cell phones, and then very important applications like space technology and nuclear technology, and in between material science, metallurgical applications, and so special coatings, engineering coatings. So, like that there is a journey slowly from atmospheric pressure down to 10 power minus 11 millibar. Millibar and tar more or less similar units. 1000 millibar is 1 atmosphere roughly, 760 tar is also 1 atmosphere. So, it is customary to use one unit throughout. So, let us use millibar, but tar is also equally popular and famous. And if you want to convert, it is very simple, 760 tar 1000 millibar. So, 1 millibar is roughly 0.76 tar. And applications, while real applications and how they look like and real details, designs, etc., we will cover them in detail, each application separately towards the end of the course after vacuum technology is completed. But right now, I will give you a glimpse or a flavor of these applications along with the physical principles involved in it and level of vacuum that is involved in it. As I already told you several times, there are some applications where only low vacuum is good enough. Low means high pressure, low vacuum means high pressure, that is 1000 to 10 millibar. Then medium vacuum is 10 to 10 power minus 3 millibar. This we have covered in the second lecture, where we have classified vacuum ranges. High vacuum is 10 power minus 3 to 10 power minus 6 millibar, and ultra high vacuum is 10 power minus 6 to 10 power minus 11 millibar. Just to give you a feeling, again I wanted to remind you, by the time we come to 10 millibar, that means the extreme end of low vacuum, already 99% of the gas is removed. 1000 millibar to 10 millibar, PV is equal to nRT. So, P goes to 1000 to 10. So, every 10 is 1%. So, only 1% is left over, 99% is removed, but it is still called low vacuum and very few applications are there. Then medium vacuum, 10 to 10 power minus 3, that means 99.999% is already removed, but metallurgy applications have not started, materials applications, plasma applications, nuclear and space science, and most important electronic applications like cell phone manufacturing, computer manufacturing, they have not started at all. So, this is a beautiful concept behind this is, when you remove 99.999% of the gas from a chamber, even then most of the high tech applications have not yet started. So, it is only the removal of that last bit of that gas that is very important. That is the first concept involved in process applications, because these lectures are mostly concepts, principles and also the applications involved in it. Earlier what we have covered is concepts like units and definitions, but right now we are covering physical situations coming out of different physical principles and their applications. This is very important because I have seen over a period of time 30-35 years when we are teaching, they are unable to appreciate which physical principle is involved in this application, what is the level, what are the precautions I need to take, which pumps to be used, what gauges to be used, what materials to be used. People are perplexed, but if you know the principles properly, then backing technologies, technological challenges, you can easily appreciate and accordingly choose according to your budget in your industry. And this is very important for those people who are working in high tech industries like electronics and space and nuclear, even in process applications like chemical and pharma. Not only that, if you want to have a startup of your own, it is all the more important that you know where to start. So, that is the reason I am giving you in these 2 lectures of process applications, I am going to cover principles and associated applications. Okay. When it comes to principles, the first principle that we will be using in applications are mechanical applications, where we are utilizing the forces due to pressure difference. All of you know, if there is a atmospheric pressure, if there is a low pressure, the P2 minus P1, that is atmosphere minus vacuum, whether it can be 1 tar or 10 tar, we will see. That multiplied by the area gives you the net force. And already I told you this force per unit area of centimeter square, roughly some 1 kg per centimeter square you can choose. So, if you can increase the area, then you will get accordingly more and more force. And right here I want to also explain you, whether you have 1 millibar or 0.01 millibar, 760 or 1000 millibar minus 1 is same as 1000 millibar minus 0.01. So, that way no point in getting very high level of vacuum if you are interested in mechanical applications like stopping a train or picking up an object precisely, or forming of vacuum forming or distillation or drying applications, etc. You are picking up. Certain applications do not require, wherever forces are involved, precise lifting in electronic industries, etc. Similarly, in drying and distillation, which is very popular in chemical applications and pharma, we will be using only the moisture removal capabilities, and also we will be utilizing the low pressure on the top of the column as the source of pulling the vapors, unlike heat driven distillation columns. Here the vacuum driven distillation columns. And associated with that, there is another physical principle that if you try to reduce the pressures, we all know in the school days, the boiling point will come down. So, there is an additional advantage by putting low pressure. On one side, you are able to create forces to pull the things in the distillation column. On the other side, boiling points in themselves are less. So, in pharmaceutical applications and chemical applications, this is very important, because long chain molecules which are being discovered nowadays for various complicated diseases like cancer, etc., they cannot be processed at low temperatures, they need to be high temperatures. And if you process at high temperatures, they are breaking chain molecules, and a broken molecule is no more a drug, it may be poison. So, how do you process them without heating, whether it is a distillation or drying? So, best is to reduce the boiling points. So, by low temperature, low pressure operation, we are also getting low temperature operation. So, low temperature processing has created like freeze drying, drying, etc. They have created a lot of scope in pharmaceutical sectors. In fact, if you visit any pharmaceutical company, you will find lots of vacuum pumps and freeze dryers, etc. So that they would like to process intermediates and all those things in medium pressure, low pressure and low temperature, so that stability is better. With environmental pollution regions nowadays, it is also important in closed room affairs, etc. This vacuum is getting prominence, because if you are heating and producing lots of vapors and lots of exhaust things are there to be managed, then that is also in trouble. So, vacuum operations in pharma and chemical industries are creating lot of giving lot of advantages for low temperature operations. Anyway, we will see when we go into those applications. So, that is the drying and distillation concept. Then thermal and electrical insulation, these are very popular examples, like thermos flask. I can use it in my lab also. Every day I can get some bit of Horlicks or hot cup of coffee, so that after 2 hours after the class I can take. So, this hotness is retained because thermal insulation, that is nothing but a vacuum insulated flask. So, we are utilizing thermal insulation concept of it. That is good enough if you put 10 power minus 3 thermal vacuums. You will not get more advantage at 10 power minus 6 minus 7, because the residual gas conduction as well as the conduction heat transfer and radiative heat transfers, which are anyway there, they are dominant. So, you will not get further advantage of thermal insulation when you go beyond below 10 power minus 3. So, these concepts have to be understood when you talk about thermal and electrical insulation. Then comes absence of oxidation. This is a boon for metallurgists, because when you are melting, casting and various operations, even in material science, when you are preparing silicon, pure silicon crystals or alloys, titanium alloys, etc., even steel industry, various aluminum or various metallic industries, alloys industries and special semiconductor industries, etc., where oxidation is going to be a problem. When we are processing these materials for realizing certain devices, you will find if you operate them at atmospheric pressure, it gets oxidized. It is of no use. We want copper, we want aluminum, we want silicon. We do not want silicon dioxide or copper oxide or any other thing, titanium oxide. We want pure materials, pure alloys. So, definitely metallurgists would like to, very fine metallurgists, very fine metallurgical products are always processed under vacuum technology. Silicon processing, silicon manufacturing, they require very good amount of vacuum. Otherwise, you end up in silicon dioxide, which is a sand. It is no more semiconductor, it is an insulator. Okay. After getting silicon material, pure materials in the form of crystalline things, slices, etc., further processing, thin film depositions, VLSI circuit, there also you require vacuum. That is processing under chip design, whereas initially semiconductor processing itself requires vacuum to avoid oxidation. Then low molecular density and long mean free path, these are two other physical concepts. They are interested in exploiting these properties in electronic industries, space technology, nuclear technology, where collisions are to be avoided totally. So, when you try to send a molecule in a particle accelerator, you take an atom and ionize it and accelerate it by electric fields and deflect it by magnetic fields, and you get different types of particle accelerators, which are the basis for nuclear fission and nuclear fusion, possible energy sources for future apart from solar. So, all the nuclear engineering heavily depend on particle accelerators, and particles cannot be accelerated in the form of ions using electric and magnetic fields in big chambers, very big chambers. We will see when we come to that implication, unless the molecular density is low, because the acceleration is lost immediately if it hits with other atoms. We want few particles on ultra high vacuum conditions to be accelerated to get various nuclear applications, which is very important for any country. It is a nuclear sector. Similarly, space technology is very important, because as I told you that most of the satellites or space shuttles will be operated at ultra high vacuum, geostationary satellites for 36,000 kilometers, etc. It is in ultra high vacuum conditions. So, how they behave, unless we simulate here, we cannot do it. So, we will not have IC chips, we will not have cell phones, we will not have laptops, we will not have space technology, we will not have nuclear technology, nuclear fusion, metallurgical things, coatings, nothing will be there unless you get oxidation free atmosphere, low molecular density, and time to form monolayer very long. That is the last concept here, so that it will have enough, it will give us enough time to do the experiments before a monolayer impurity layer is formed, and a long mean free path can be exploited for proper controlled deposition of thin film coating units like molecular beam epitaxy units for various high tech applications. So, what we have seen here is force concepts, drying concepts, distillation concepts, long mean free path, thermal and electrical insulations, for example, high voltage transmission lines, people use vacuum interrupters. High current, high voltage cannot be interrupted, because it will create discharge, then spark or arc. As intensity is going more and more, it will become lightning, and entire substation may burn. So, with such a huge amount, 220 kV, thousands of amperes of current, you cannot open it unless you open it under vacuum, because it will create a big explosion type of thing because of lightning or heavy discharge of few amperes type of thing under high voltage. So, electrical insulation, thermal insulation, long mean free path, controlled depositions, absence of oxidation, and molecular density very low, so that no scattering takes place. Very long time of monolayer can be formed, like in scanning electron microscope. If you do not have a long time for monolayer formation, you will get, instead of studying interfaces and surfaces in biotechnology or nanotechnology or advanced material science, we will be studying its impurity layers. So, oxidation will be formed in few seconds. We need 1 hour to do an experiment in an analytical instrument to take a topology or chemical things like XPS or SM or TEM. We need a very good amount of ultra high vacuum. Then only we can study surfaces interfaces. That is time to form monolayer. So, these are the concepts involving low vacuum in certain applications where forces and drying etc. medium vacuum, then high vacuum for metallurgical and material science type of things, or coatings or solar energy, solar coatings or PV, solar PV etc. But when you go to electronic space nuclear, very purity is very important, parts per minute, parts per million type of thing, and a very high, very ultra high levels of vacuum are required to avoid collisions and to avoid oxidations. So, high, ultra high belong to high tech applications, low and medium belong to little average applications, but huge volumes are involved here also. Let us see these things how they look like. First, let us see low tech applications, but very important for day to day life, involving low vacuum and medium vacuum. Here the low vacuum, let us see. The forces that we see here, you can lift any container with suction caps and holding it, lifting it, transporting it. These are regularly used in packed products etc. before they are sent to customers, and this is also equally important to lift large scale wooden panels or even glass panels. Very important to use very nice uniform lifting arrangement. That is possible by utilizing pressure difference created by vacuum on one side, and other side natural thing is available atmosphere, anyway we can lift it. So, this sort of controlled precise lifting is possible. So, once you lift you can transport it. For example, here you will see some biscuit packets or chocolates, they are lifted using vacuum clutches and they are also transported. That means there is a constant vacuum line connected with several ports, and each port will pick up one biscuit packet nicely and they can be transported in an automation industries. Automation, you can use it, industrial automation. It is possible only because of vacuum. You cannot use pneumatic things here and all, because they are little cumbersome, and also one side P2 minus P1, that force, no? That already P2 atmosphere is naturally available, we do not have to create an atmosphere. So, we can create controlled vacuum P1 and the difference multiplied by the area will give us forces. If you come here, you will see the effects of vacuum sucking. Here on one side you produce vacuum, on the other side atmospheric pressure. So, this sort of techniques are routinely used to produce forming in plastic industry, etc. Same thing is used in packaging of food products, and in day to day life we are using these force concepts even in our vacuum cleaners. So, right from the coffee that we take in the morning, vacuum cleaners that we use immediately, the TV, cell phones that we are using, almost every walk of life we are using vacuum. And this force application is also used in stopping a multiply connected flexible trains, for example. A single body type of automobiles can be stopped by a pneumatic brakes, etc. But a multiply connected things can be stopped by utilizing the natural forces coming from atmosphere and other side vacuum. So, other side, whether it is 1 tar or 10 tar or 0.1 tar, uniform force will be there in all the compartments when they are when the driver makes a brake. So, vacuum brakes are very important to have a uniform braking when the train is moving at very high speed, which is not possible by mechanical brakes, because there is a relative momentum. Then you can immediately understand when high speed train is moving and the driver is suddenly putting a brake, and that means it is instantly trying to come to stop, and the last bogie is still in full momentum. And I think sometimes, to have a joke, that is the only time where the guard will come because of huge force, he will jump all the way before to the driver. So, to avoid such things, these vacuum brakes, nowadays pneumatic brakes are also applied. Similarly, in vacuum impregnation, when high voltage coils, etc., when they are impregnated, people utilize vacuum to make this impregnating liquid to go into the interior as small nook and corner of various portions in the internal windings, etc. So, that you will have a uniform impregnation, which is very important, because these high voltage operated transformers, coils and all, unless you impregnate it properly to avoid electromagnetic forces, because high currents and high magnetic fields will produce lots of forces. So, people impregnate it. That impregnation should be done properly, and it should be degassed, it should not have moisture. We will see when we go to the electrical applications later. So, these also utilize the mechanical force applications. Then comes to the medium applications. Medium application, they do not use the concept of force, but they utilize some other concepts. What are those concepts? In bulb, for example, heat transfer concept. If there is a bulb, there is a filament, you try to pass current, I square R, it produces heat. But unless you surround it by a bulb and remove the air, convective heat transfer will immediately make the filament cool down, and it can never become red hot. And even if you try to pass more current, because of oxidation, it will get cut. So, to avoid oxidation, to increase the temperature, so that you will get lighting effects out of heating, and to reduce the heat transfer due to convection, people use these vacuum in incandescent bulbs as well as fluorescent bulbs. Okay. You try to evacuate and then fill it with some gases, etc., gas filled tubes and all. We will discuss it separately when we deal with electrical application. Okay. So, thermos flask I already discussed. This is also a heat transfer application. Inner and outer vessels are there, annular space being evacuated. You get very good amount of thermal insulation, and hot cup of coffee stays for hours together because there is no heat transfer, excepting the solid conduction and radiation, which are much less compared to convection. Similarly, in vacuum distillation I have already discussed in the principles, the refluxes are created by vacuum. So, it is a vacuum driven things, and the distillation columns are user friendly and also environment friendly. They are becoming very popular in oil refineries and pharmaceutical sectors and chemical sectors. Lack of time today we will not discuss all those things, but we have a separate section for it, for chemical, pharmaceutical, etc. In food processing, even in pharmaceutical or for freeze drying is very much used, because freeze drying is not drying alone. You try to freeze it and then sublime the moisture. That means it requires a very good level of vacuum of 10 power minus 3 torr, because very few molecules are coming under vacuum. And if you can do that, the fluffiness of cake can be retained. So, there are various other properties in food processing and pharmaceuticals. We will discuss these things in freeze drying. Similarly, freeze drying of coffee that we see, what we are melting and finally making a liquid slurry of coffee, and then try to put it in a chamber where you apply vacuum, so that moisture can be removed even at atmospheric pressure and even at atmospheric temperatures, because pressure is reduced, boiling point is reduced now. So, immediately you will start getting water out, dehydrated products. You will get a very fine powder without any moisture content, and when you mix again water or hot cup of milk, then instantly it becomes instant coffee. So, all these mundane applications are pharmaceutical applications, or food processing applications, or heat transfer applications, or even mechanical applications. Most of them use low and medium vacuum. So, with this introduction of low and medium vacuum, utilizing thermal aspects, mechanical aspects, drying aspects, moisture removal aspects, and little bit of oxidation avoiding aspects, we have created several process applications. In the next class, we will try to cover high-tech applications like metallurgy, material science, plasma, nuclear, space technology, and manufacturing IC chips, and also TVs, plasma TV or LCD, LED TVs, and other X-ray tubes for medical applications. So, all these high-tech applications utilizing high and ultra-high vacuum, we will try to see, and that time also we will understand what are the physical principles involved in that. So, this way this lecture 4 and lecture 5 will give you a glimpse of various industrial applications which are very much needed for our day-to-day life, along with physical principles associated with vacuum technology. Thank you very much.